What's going on, team? This is going to just be a quick video lesson, a few examples for section 2.6, just solving polynomial equations by factoring. So let's just jump right into it. So the first kind of method we're going to talk about is factoring by grouping. And so really what you want to do in these type of problems, you want to kind of recognize, and sometimes this may require some reorganization of the problem. And not all polynomials will work out this way. But kind of my goal here is to solve this equation. I'm going to find all the roots. So I kind of split them up into two pairs here. Those first two terms is my first pair, and the second two terms is my second pair. I can kind of pull out a common factor from each. So if I pull out a common factor from x cubed and 5x squared, I would pull out x squared and be left with x plus 5. Over here, when I have the minus 4x minus 20, I can pull out a negative 4. Be very careful here. Since you pull out a negative 4, it's going to be plus 5 over here. Negative 20 divided by negative 4. Cool. And so now we notice that we kind of have two matching terms here. We have those x plus 5s from each. All right, so what you really are kind of doing here is you're pulling out a common factor of x plus 5. So I can rewrite this as x plus 5 times x squared minus 4. All right, both of those terms are being multiplied by x plus 5, so we can just pull that out front, very similarly to how we just pulled out an x squared, or we pulled out a negative 4. From there, just got to finish factoring it. I can factor that x squared minus 4 as just x plus 2, x minus 2, difference of two squares. And then I'm set to get all my roots. So we'll have x equals negative 5, x equals negative 2, and x equals positive 2. So as I said, not all polynomials will work out this nicely like this, but if you do kind of recognize, maybe I can try pulling out some common factors. If I kind of split it down the middle here, and you get this, you're able to get the same term for each, then factoring by grouping is a great way to do it. All right, so the second example here is just another kind of a special case. It's kind of if they have a quadratic form. So what you're going to do here is it's going to happen when you have just an x to the 4th, x squared, and a constant. What we're going to do is, this is actually a quartic, but we're going to kind of force it into a quadratic. So what I'm going to do is make this substitution right here. I'm going to make y equal to x squared. So then what I can do is I can rewrite this quartic as 2y squared minus y minus 3. All right, so now let's just solve this quadratic. You can solve this quadratic however you like. You can factor it, use a quadratic formula, complete the square. This one's actually factorable, so I can write 2y minus 3, y plus 1. And we'll get y equals 3/2 and y equals negative 1. All right, so we're not trying to solve for y. We're trying to solve for x. So we need to substitute back in for x squared here. So x squared equals 3/2. X squared equals negative 1. All right, now I just need to square root both sides. So take the square root of both sides here. And the main thing you got to remember, whenever we take the square root of both sides, we need to add a plus or minus. So this is plus or minus the square root of 3 over 2. Same thing over here. X will equal plus or minus I. If you want to simplify this square root, this plus or minus square root 3 over 2, we can just rewrite that as plus or minus root 6 over 2. We multiply the top and bottom by root 2. So then we have 4 roots, 2 real ones, and 2 complex ones. So as I said from the start, this is really only going to work if it's in this format here. You have a quartic term, a quadratic term, and a constant term. It's not gonna work if you have a cubic term. Not gonna work if you have a linear term. All right, so when it does work, as you can see, it works out very nicely. And you can also, if you have it in this form here, you can also just do the quadratic formula. The way that's going to work is you're just basically going to be solving that entire thing. That'll make it be equal to x squared instead of x. So basically you go through, find your roots from the quadratic formula as you normally would, and then do the same thing. You're just going to need to square root both sides to find the values of x as opposed to x squared. All right. And then this is really going to be the real meat of this section. When all else fails, we're going to have to try and factor things using what's called the rational root theorem. And so the rational root theorem is really what's just going to give you a list of possible roots. All right? And then we kind of have to do a little bit of a guess and checking to try and kind of figure out what the actual roots are. So the way it works is if you have a polynomial, so remember polynomials are just things written like this. Okay, you can generate a list of all the possible roots by taking the factors of the constant term, and the constant term is just your last term over here, the constant, no variable on it, and the divided by the factors of the leading coefficient, which is just the coefficient on your highest degree term. All right, so really, it's the factors of that constant term over the factors of the coefficient. Okay, and usually we call the factors of the constant term, we call those values p. The factors of the leading coefficient, we call those q. So really to kind of generate our list of roots, it'll be kind of, we'll just call it p over q. So here's an example down here, kind of, we have this polynomial. And remember, what are the possible rational roots? So this is not guaranteeing that all of these are going to be roots. It just kind of takes our lists from an infinite number of possibilities to, as you can see here, like 10. So what we do is we get the leading coefficient, which is 6, all the factors of 6, so plus or minus 1, plus or minus 2, etc. Do the same thing with the constant term, plus or minus 1, and plus or minus 3. So then we take all those and just do p over q. Okay, so here are the values of p over here. Here are the values of q. And we get the list of all the possible rational roots here. So that's how the rational root theorem works. You're probably asking, all right, so I got the list, what do I do now? Well, let's see an example and kind of work through it and kind of see how we would approach it. All right, so we're going to use that rational root theorem here, and what we'll find is it's basically a game of guess and check, trying all those roots. We're going to find all the roots of this polynomial here. So the first thing we're going to do is we need to get all the values of p and all of the values of q. So remember, all the values of p are going to be the factors of our constant term over here. So that'll be plus or minus 1, plus or minus 2, and plus or minus 4. Q is going to be all of our factors of our leading coefficients right here, which are just going to be plus or minus 1 or plus or minus 3. So the list from what we're working with, the possible rational roots, and remember there may be some roots that are irrational that we will not be able to solve using this method. But the idea is hopefully we can kind of get it down to a quadratic, and once we have it as a quadratic, we can get the irrational roots if there are any. So the possible rational roots p over q, you're basically just taking every combination of p divided by q. So first plus or minus 1 over 1, plus or minus 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. All right, great. So what I'm going to do now is, it's unfortunately a little bit of a tedious guessing game here. I'm going to start with +1 and basically just trying to do a kind of form of synthetic substitution to check if these are roots. So I'll take my coefficients here, 3, 13, 15, 0, -4. Don't forget the 0, there's no linear term here. And basically just determining if these will be roots. So doing quick here. All right, and so remember, all you're looking for is if that last value is 0. All right, if it's 0, it'll be a root. So 1 is not a root. Let's keep it moving. Let's do -1. So same thing, 3, 13, 15, 0, -4. Hopefully I don't mess up my arithmetic, because I'm known to do. All right, close, but no cigar. We need 0, not 1. Let's move on to +2. Whew. All right, definitely not. Very far away. Let's try -2. Hopefully we get lucky here. So we'll have 3, -6. Boom. All right. So that means that -2 is a root. We've already eliminated these ones. So what we've been able to do is we've now been able to kind of factor this polynomial down. We can factor out an x plus 2, because we know -2 is a root. And then these are going to be the coefficients of the resulting cubic. So 3x cubed plus 7x plus 1. I'm sorry, 7x squared plus 1x minus 2. And so let's kind of take this over to the next slide. So now we got to kind of keep moving and try and factor out one more so we can get it down to a quadratic. So we have x plus 2 times 3x cubed plus 7x squared plus x minus 2. All right. And so where I'm going to start, I've already eliminated -1, I've already eliminated +1, and I've already eliminated positive 2. I'm going to check -2 again, because just because it's a root, it could be a double root. So we need to check it again. I'm going to check out my cubic just to make sure it's not a double root. So 3, 7, 1, -2. My new coefficients is that cubic right there. I'm going to do the same thing. So this carries down. Oh, beautiful. So it is a double root. So now we can further factor this polynomial. It'll now look like x plus 2 times x plus 2. So these are the coefficients of the resulting quadratic down there. And I guess I can write that as just x plus 2 squared. All right. So remember, the initial goal here is we need to find all the roots. Well, now that I've got it down to just a quadratic, I am going to completely ditch the rational root theorem. I'm not going to spend any time plugging in any other values, because for one, they might be irrational, and this rational root theorem will miss them altogether. 2, we have a much more efficient way to solve quadratics. In this case, I'm just going to use the quadratic formula, because that is not going to be factorable. So my roots there for that quadratic, -1 plus or minus. So we'll have -1 plus or minus 1 plus 12, so 13. over 6. All right, so our roots are going to be, there's two roots right here, -1 plus or minus the square root of 13 over 6, and x equals -2, which, as we mentioned, is a double root. All right, so that's all we got for today. Just kind of, as you see, it works pretty tediously, but kind of the overall process is not so bad, as long as you're very comfortable using synthetic substitution. So thanks, and see you guys later.